talk is on the experimental and theoretical developments in Lagrangian coherent structures and how they apply to geophysical transport. So this work is largely motivated by trying to track hazardous spreads. So if there was a release of hazardous materials, such as at the Fukushima disaster, is there some way we can track or predict where that material is going to go? And one way you could try to do that is to look at the wind velocity field. So if you were to look at the wind velocity field, you get an idea of the direction where material is likely to transport to, but it's kind of hard to tell where it will converge to. And luckily, with dynamical systems theory, we have a lot of nice tools where we can detect Lagrangian transport structures that predict where particles and material within a fluid flow are going to converge. And so this is the backward time FTLE field with an integration period of 24 hours. And it gives a measure of how much particles are stretching in backward time. So stretching in backward time is convergence in forward time. And the regions in yellow are regions where the FTLE value is high. So there's a lot of spreading in backward time. So in forward time, we would expect particles and material to converge along those bright yellow features. And you can see there's actually one here off the coast of Japan. So this wasn't for the time of the Fukushima disaster, but if there was a disaster on this day, you might want to pay attention to that region. So this work can be broken up roughly into three separate parts. There's a theoretical component where we analyze equations and put forth some new ideas. There is a numerical part where we ran numerical simulations to test some ideas on how to detect Lagrangian transport structures. And there was an experimental component. Some people who are much braver than I am went out into the field and actually sampled wind velocity data, and then they passed that on to me for analysis. So Lagrangian transport structures come from this dynamical system. dx dt is equal to the velocity field, simple ordinary differential equation with an initial condition. And traditionally, this system has been analyzed using Lagrangian methods, where we integrate the velocity field over some time period of interest, and that gives us the flow map. From the flow map, we can then calculate the Cauchy-Green tensor, which gives us a measure of objective strain within a body. And the Cauchy-Green tensor C has ordered eigenvalues lambda 1 through lambda m, each with its own eigenvector. So one way we can use this to look for Lagrangian transport structures, as I mentioned before, is to look for regions where the FTLE value is high. So here's the FTLE here, and it comes from the largest eigenvalue of the Cauchy-Green tensor. And another way we can look for Lagrangian transport structures is through Lagrangian coherent structures. And there's different ways to define Lagrangian coherent structures. But the way that we're fond of is to look for a special kind of ridge of the FTLE field. So it's a codimension 1 material surface in the FTLE field that satisfies these three conditions here. So first, the FTLE value has to be positive, so things are actually spreading. This is a critical point, so either a min-max or a inflection. And then this is a concavity condition. So it just says that we want a maximum. So it's got to be concave down. Recently, there have been some new developments in how to analyze this dynamical system and look for Lagrangian transport structures. And those methods involve the Eulerian rate of strain tensor, which comes from the gradient of the velocity field. And the Eulerian rate of strain tensor S has its own eigenvalues, S1 through Sn, each with its own eigenvector. And we call the minimum eigenvalue, S1, the attraction rate, because it gives you an instantaneous measure of particle convergence. And we call Sn the repulsion rate, because that gives you an instantaneous measure of particle separation. So for the theoretical work, this work was largely interested in trying to better understand these new Eulerian methods. So it's only recently that the Eulerian rate of strain tensor has been used. I think the first paper published was back in 2016. So there's still a lot we don't know about it, and we wanted to try and advance that. And we had some interesting results. We were able to prove mathematically that S1, the minimum eigenvalue, is the limit of the backward time FTLE. We were able to prove that the repulsion rate, Sn, is the limit of the forward time FTLE. And this is as the integration time goes to 0. So as the period over which you're integrating goes to 0, the FTLE will converge to these eigenvalues. We also managed to prove that the eigenvectors of S are equal to the eigenvectors of C in the infinitesimal limit. So as integration time goes to 0, the eigenvalues converge, or eigenvectors converge. We also derived higher order approximations. Excuse me, getting over a bit of a cold. So we managed to derive higher order approximations. So S1 and Sn are the limit. So that gives us like a 0th order approximation. And we were able to derive first order and second order. And the methodology that we developed for that can be applied to go to nth order. We also developed a new Eulerian diagnostic. So previously there was the attraction rate and the repulsion rate, the eigenvalues of S. There was also a trajectory divergence rate that I'll talk about later. And another one, objective Eulerian coherent structures, that was developed back in 2016. And we developed our own new method called infinitesimal time Lagrangian coherent structures. Finally, we applied these new diagnostics to analytic and geophysical flows. And this work is part of a paper that is currently in preparation for submission to the Journal of Nonlinear Dynamics. I think I have about one last example we have to work on, and then I'll be ready to submit in the next couple of weeks. So, to dive into this, if you look at the Taylor series expansion of the Cauchy-Green tensor, you get this term here. We find that to a leading order, to a first order, it's a multiple of the Eulerian rate of strain tensor. So using this Taylor series expansion, along with some properties of eigenvalues, and I think some properties of the Taylor series expansion of the log function, we were able to derive this second order FTLE approximation. And part of this derivation also proves that the FTLE, the forward time FTLE is, or Sn is the limit of the forward time FTLE. So you see the FTLE here, we have Sn, and then as these terms go to 0, you're just left with Sn. And then we also managed to derive, for the backward time FTLE, found that it's negative S1 with this linear and this quadratic term. And the lambdas in this term come from the matrix perturbation equation down here. So now that we had these approximations, we decided to try applying them to an actual flow. So we looked at the nonlinear saddle. It's the simplest nonlinear fluid flow you can get. And we got really good results for this. So you can see in blue here, that is the root mean square error between the FTLE field, the backward time FTLE field, and S1. And then here we have the root mean squared error between the FTLE field and the first order approximation. And here we have the FTLE field and the second order approximation. And as we expected, the higher order approximations in the infinitesimal limit give better results. And if you look at it in a log-log space, we see they have slope 1, slope 2, and slope 3, as we would expect. So with that success, after looking at the eigenvalues of S and showing that they're the limit of the FTLE, we thought, what can we say about the eigenvectors? So looking at the proof of how the eigenvalues are the limit of the FTLE, and looking at how the Cauchy-Green tensor, the series expansion of the Cauchy-Green tensor, we were then able to prove that in the infinitesimal limit, the eigenvectors are equal. So here's the proof here. We start off with an eigenvector of S, and then this is just a simple balance of equations. Then we get this term here, which comes out of the Taylor series expansion of the Cauchy-Green tensor, and this term here, which comes out of our proof of the FTLE field. And then that simplifies into, in the infinitesimal limit, C and an eigenvalue of C. So with this, then we decided to go back and look at, what's the definition of a Lagrangian coherent structure? So it's a material surface that satisfies these three conditions. And we've proved that sigma, that the limit of sigma in the infinitesimal limit is S1 and Sn. And we also proved that the eigenvalue of C, eigenvector of C, is also the eigenvector of S. So substituting in the Eulerian terms, we were able to derive infinitesimal time Lagrangian coherent structures. So negative S1 is the limit of the backward time FTLE field. So instead of looking at negative S1, we look at just S1. And so we look for troughs of S1, so regions where material is instantaneously converging. We look to make sure that it's a critical point. And because it's a trough, we look to make sure that it's concave up, so it's a minimum. And then we were also able to define repelling ILCS. So Sn has to be greater than 0, so material's diverging. It has to be a critical point, and it has to be a maxima, so it has to be concave down. And then we decided to apply this. So this is an application of ILCS to a wharf model simulation over the southeastern United States. So here's the initial configuration. In blue, the blue lines are attracting ILCS, the red lines are repelling ILCS, and the cyan circles are just passive tracers moving with the flow. So this is the initial configuration, and this is 2 hours later, 4 hours later, and finally 8 hours later. And we can see that material has diverged from the repelling ILCS, and that they've collapsed onto the attracting ILCS. Now, one of the interesting things we noted about this was that we have a lot of these repelling ILCS at the initial time then get absorbed by the attracting ILCS later, and we thought that was really interesting. So when we looked at the attraction rate and repulsion rate field, we figured out why this was happening. So here we have the attraction rate field, and here we have the repulsion rate field. And just looking at them, looking at the color bars, we can see that the attracting structures in the attraction rate field are more than twice as attractive as the repelling structures are repulsive. So from this we concluded that the repelling structures are repelling, they're just being overwhelmed by the attraction of the attracting structures. So we had this in 2D, and then we decided to expand it to 3D. A lot of the previous Eulerian diagnostics had only been done in 2D, so we wanted to kick it up a notch. So the blue is an attracting ILCS, and the green blob is a blob of passive tracers. And this is just in a three-dimensional version of the double gyre flow. So if we look at the initial configuration, we see that the green blob is a perfect sphere straddling the attracting ILCS. And after they've been advected with the flow, the blob has converged onto the manifold, and as expected. So then we also looked at repelling, and this one never wants to work for some reason. So we can see in this that blob of particles initialized around a repelling iLCS stretches away from it.
We're going to go back to that real quick, Peter.
Oh,
Question.
yeah, sure thing.
So is that repelling ILCS actually rotating, or is it stretching? What is it doing in that image?
So it's being advected with the flow, so it's coming down, it's like collapsing down against the wall, and then it's also moving with the wall, and it's kind of twisting a bit.
Twist, okay.
Yeah, I think you'll see that a little bit better. Yeah, so here it is at the initial configuration, perfect sphere along the manifold, and yeah, so it kind of bends a bit with the flow. Yeah, and here it is later on, and the blob has spread away. So some advantages of these new methods that we developed are that it's valid for n-dimensional systems. So as I mentioned before, a lot of work on these Eulerian methods have been done for 2D. Now we have a method that works in n dimensions, not 2D or 3D, but however many dimensions you want. There's no need for time-consuming trajectory integration. So one of the big drawbacks with Lagrangian methods, like the FTLE, like LCS, is that you have to integrate particle trajectories. And it's very time-consuming, it's very expensive. With this, you're just looking at gradients of the velocity field, so you don't need a computing cluster, you can do this on your laptop. Also, because it doesn't need we don't need to integrate particle trajectories, you don't need a highly defined velocity field. So if you're integrating particle trajectories, you need to know the velocity field over a large enough domain with enough resolution that you can accurately integrate the trajectories. But this, being based on gradients, can be done with very sparse data sets. In fact, you can do it with as few as n+1 points. So in a 2-dimensional space, you only need 3 points. In 3-dimensional space, you only need 4. So on to the numerical work. So the purpose of this work was twofold. Just to see if, first, we could measure local Eulerian diagnostics using a single fixed wing UAS. This was done through numerical simulations of a fixed wing UAS. And we also wanted to know if you have Eulerian, if you have local Eulerian information, can you use that to infer the Lagrangian characteristics of a flow, such as the passing of an LCS. And for this, some results from this, we developed a new algorithm to be able to calculate the gradient of a field from measurements along a circular arc. I've looked into it, and I was surprised that apparently this hasn't been done before, or doesn't appear to have been done before. We demonstrated that if you have a single fixed wing UAS, you can get an accurate approximation of your local Eulerian diagnostics. We showed that with local Eulerian diagnostics, you can detect the passage of LCS. And then we also double-checked just to see if you can use the Eulerian diagnostics as measured from a simulated UAS to infer the passing of LCS. And this is part of a paper that has been submitted to the journal Sensors. It's currently under review, and hopefully we'll hear back from them soon. So in this work, we do look at the attraction rate to try and detect the passing of Lagrangian coherent structures. But we also use the trajectory divergence rate that was developed in this paper with Gary Nave that was published this year in the Journal of Nonlinear Dynamics. And one way to think of the trajectory divergence rate is that when it's negative, streamlines of the flow are converging. And when it's positive, streamlines of the flow are diverging. So it gives you a nice scalar measurement of how much traction or repulsion is going on in your flow at a given instant. the algorithm we developed to calculate the gradient just assumes that we have a circular arc here, and we're taking measurements along an arc, and we have some coordinate frame that we're interested in, x and y. And then with these measurements, we can use central finite differencing to calculate the gradient at the origin. So we have this point here and this point here, and we can use measurements from those to calculate a dx prime. And from measurements here and here, we can calculate dy prime, and then we just apply a rotation to put it into the reference frame we're interested in. And using this algorithm, we were then able to calculate an approximation of the trajectory divergence rate. So we see here those results. In red is the true trajectory divergence rate. So at a singular point, what is the trajectory divergence rate? Then the blue is for a perfect circle, a perfect circular arc around that point. And finally, the black is for a simulated UAS that's being knocked around by the wind and trying to maintain its orbit. And we can see that the simulated flight and the circle are right on top of each other. So looks like being knocked around by the wind and trying to maintain course doesn't have that big of an effect on our approximation. And we also see that for smaller radii, we get a really good approximation. And then as the radius increases, the approximation falls off. And here are the results for the attraction rate field. So once again, the red is for the true at a point, the blue is for a perfect circle, and the black is for a simulated UAS. And we see that at small radii, once again, we get a really good approximation, and then that approximation falls off as the radius increases. So now that we could measure the local Eulerian diagnostics, we wanted to know, can we now infer the passing of a Lagrangian coherent structure? So here is kind of a schematic demonstrating our idea. So if you have a Lagrangian coherent structure passing by and you have a point, can you detect the Lagrangian coherent structure within some radius of that point? And we use different threshold radii because of the discrete nature of numerics. So we set up a simple classifier and with a true positive and false positive, and this gives an idea of what a true positive is and a false positive. So on this side we have a true positive. We say that if the value of our Eulerian diagnostic is above some threshold, then that's a positive, and if it's below a threshold, that's a negative. So here in the yellow and green, those are regions where our Eulerian diagnostic is above the threshold. And the white are regions where it's below the threshold. And the blue lines are attracting LCS. And we can see here that there is an attracting LCS within our threshold radius, and that the attraction rate field, or our Eulerian diagnostic, is above the threshold. And then here, we see that at the center of our radius, the Eulerian diagnostic is above the threshold once again, but there's no LCS within the radius. So this would be a false positive. And then we can evaluate the classifier using what's called a receiver operating characteristic curve. And this gives you an idea of how good your classifier is. So for different threshold levels, you start off at a threshold of 0, and you go up to a threshold of 100%. And if you have a good classifier, it should follow this arch more or less. It should get close to this one. A perfect classifier, you can also quantify this using area under the curve. And a perfect classifier would have an area under the curve of 1. The dashed line gives what you would get from random guessing, and that would have an area under the curve of 0.5. So worst sensor you can have is around 0.5. And here are some results for that. this is if we have this is for the trajectory divergence rate. So if we're measuring the trajectory divergence rate at a single point, can we detect the passing of LCS for various threshold radii? And we give the area under the curve in the legends in the box, and we can see from this that yeah, for smaller radii, you can detect Lagrangian coherent structures. It's not perfect, but it's a start. And here's the results for the attraction rate field, and we see these are much better. We're seeing area under the curve close to like 0.85. So yes, we can, if we have the Eulerian diagnostics at a point, we can use that to infer the passing of LCS. And then just to kind of bring this home, this is the trajectory divergence rate as measured from a simulated UAS. So if we have a UAS circling an area, can we detect LCS? And once again, yeah, we can. And with the attraction rate field, yeah, definitely. We're seeing area under the curve once again around 0.85, so that works. So some advantages of this methodology is that there's no need for multiple operators. I know that one of the problems with doing UAS flights now is that all the operators need licenses. So with this, you only need one person. It's highly portable and can be deployed on short notice. So there's other ways to get wind speed measurements like LiDAR and SODAR. They can be heavy, they can be bulky. You can have a small UAS that fits in a backpack. And once again, no need for trajectory integration. So finally, just to touch on the experimental work that I helped with. The aim of this was to see if we could apply Eulerian diagnostics to real-world wind speed measurements, and if we could then detect Lagrangian coherent structures. And so for this, we applied the attraction rate field to a real-world wind speed measurements that were measured using UASs and wind towers. And then we compared this to the simulation, to a numerical simulation. So with the real-world measurements, we only have them at a small point, so we wanted to know, well, what's going on in the bigger scheme? And we did find indications of LCS. This is part of a large collaborative work that was published in the journal Sensors last year. So last summer, there was a big field campaign in San Luis Valley, Colorado, that David Schmally and Javier were at. And they were out there sensing the wind speed. And so here's, so you can see here's one UAS, a fixed wing quad rotor, or not fixed wing, a quad rotor UAS.
Good fix.
And there's another one in the background that you can't really see. And here's a tower. So from those 3 points, we can construct a triangle and then interpolate to an internal point in that triangle to calculate the gradient of the wind field, which we can then use to calculate the Eulerian strain tensor. So to give you an idea, a sense of the scale, this is where the sampling was done. It's at Leach Airport in Colorado, and we used these 3 points and interpolated to that internal point. And this is represented by the red dot here. So this is from the numerical weather simulation over the entire valley, and you can see that there's effects from mountains off to the side here, and there's a lot of convective activity going on, and then towards the end a front passes through the area. So this shows the attraction rate. In blue comes from the numerical weather simulation, and the orange comes from the measurements, the experimental measurements, and then the gray is just some uncertainty bounds that we put on it. So as I mentioned before, towards the end, there's a front passing through, and that seems to correspond pretty well to that, that dip there towards the end. And this yellow bar is a slide that I'll show, is the time period of a slide that I'll show in a minute. But we also see this large dip here around 1400. So we were curious, well, what's going on around 1400? So looking at the field for that time snapshot, according to the WRF model, or not the WRF model, I'm sorry, the numerical weather model, there's a lot of convective activity going on over the field during that time period. So what we think we're picking up is an indication of a convective plume. And there's likely an attracting LCS associated with that convective plume. And here we have at 1550, and we can see here that there's a front passing through, and there's likely a Lagrangian coherent structure associated with that front. And it's passing right by the right by our sensing area, right as we see that dip. So we concluded from that that we are picking up indications of an LCS. So some of the advantages from this work is that's the first real-world use of UAS measurements to detect Lagrangian coherent structures. And this is applicable to other sensor platforms. So the methodology we developed doesn't have to be a UAS. It could be, you could use a LiDAR, you could use a SODAR. So just to wrap things up and conclude, in this work we proved that there's rigorous mathematical connections between Eulerian diagnostics and Lagrangian diagnostics in n-dimensional systems. I want to make that clear. We also formulated a new Eulerian diagnostic, infinitesimal time, LCS. We explored the ability of Eulerian diagnostics to detect Lagrangian coherent structures. We developed a new method to use a single fixed wing UAS to measure the local Eulerian diagnostics of a system. And we also applied these Eulerian diagnostics to real-world experimental measurements and detected indications of LCS. And my work has gone into several conference presentations, most notably an upcoming presentation at the Siam Dynamical Systems Conference at Snowbird. I've also contributed to a couple of papers. One's with Gary Nave, which was published this year. One with Zhuping Zi, that is currently under review. And another with Javier, that is still in preparation. And I have a couple of first author papers. First was that big collaborative effort that I just talked about. That one was published last year in the journal Sensors. The one for the fixed wing UAS is submitted. We also have one on the theoretical work, and that's almost ready for submission. And finally, we have one on the on atmospheric pollution patterns, and hoping to get that submitted by the end of May, beginning of June. That's my talk. Thank you.
So we'll take questions from the non-committee audience, including those online. But anybody, feel free to ask a question.
Yeah, Peter. So you were talking that you mentioned that you could use any type of sensor, but what's for detecting a structure? What's the minimum temporal resolution that you need? And I asked that because when so you mentioned SODAR and LiDAR, and so those obviously have a lower temporal resolution compared to something like a sonic anemometer or
So it depends on the time scale of the structures you're looking for.
Okay.
If you want a structure that's like a 2-hour-long structure, you're going to want a much more higher resolution data set than if you're looking for a 24-hour structure. So we've used, numerically, we've looked for these things using weather models, and the resolution on that is 1 hour.
Okay.
So, And we have found interesting results with that.
So in the theoretical part, you said your method can be applied to higher dimensional fluid.
Yes.
And can you give some examples?
Well, I showed for a three-dimensional system, we haven't actually applied it to a higher dimensional system yet, but the math holds for however many dimensions you want. So I know there's some dynamical systems that, the ones that you look at, aren't they four-dimensional? Yeah. So you could apply them to your systems. To look for,
There we go.
I've got a question. I don't know if this can be heard.
I can hear you.
So you showed, speaking of these higher dimensional flows, you showed some nice pictures of two-dimensional iLCS early on.
Yes.
How do you talked about a little bit about how you defined a trough. How do you define a trough or a ridge in 3D?
It is a codimension 1 material surface that satisfies those conditions.
Okay.
That's
And
how I define it.
Yeah. It was second.
Yeah.
Okay.
It's very easy to visualize a ridge in 2D, but when you're getting into like higher dimensions, they become hypersurfaces,
Right.
and our
Right.
brains are not equipped to visualize.
Are there any codimension 2 surfaces, or is it defined to be a codimension 1 surface?
We define it as a codimension 1 surface.
Okay.
I imagine you could have iLCS embedded within iLCS, and that would be a codimension 2, but
Okay.
I'm not sure how much a codimension 2 structure would have on the overall flow.
Okay.
No. But it might be useful for visualizing effects on the iLCS itself. So you
Right.
might have like a slow-fast system.
Right.
Huh.
Anyone else? All right, if not, I'm going to ask other committee members to and sign off.
Good job, Peter.
Thanks.
Peter.
All right, it was under 45 minutes.
Okay.